All right, ladies and gentlemen, thank you very much for downloading this web lesson. It's just a quick little worksheet that we're going to work through while you guys are at home for the snow day. I do appreciate you taking the time to download this video. It's really going to help us staying on task and on the schedule. So your homework for tonight is going to be the homework that you guys see on your calendar. Today's a little bit of a change from what we were doing over the past couple days. Today we're talking about exponential functions, which you could see from this worksheet here. If you have not printed out a copy of the worksheet that you see in front of you, you might want to go back to my webpage and print it out quickly so you can work along with me. We're not talking about inverse functions at all today, which makes it a little bit easier, and we're just going to be talking about exponential functions, which you guys are already um, somewhat familiar with. So let's take a look here. For problem number 1, I have two functions. My first function is f of x equals 2 to the x power, and my other function is g of x equals 1/3 to the x power. So they're both exponential functions, and what I mean by exponential functions is a function f of x equals a to the x power, where a is a real number. And in fact, we really want to restrict a to positive numbers. We have two different kinds of exponential functions. One where our a value, the base of our exponential function, is a whole number, and then we have another one where we have a fraction. And we could go ahead and we could try out this first one. I have a little keyboard icon covering it, but part A is f of 3. So that means we just input the number 3 into the function f. So 2 to the third power, which equals 8. Same idea for g of 2. 1/3 to the second power. Well, that means the 1's going to be squared and the 3 is going to be squared. That's 1/9. F of 0 is 2 to the 0 power, which you guys all know that any non-zero number to the 0 power is equal to 1. We could keep trying a couple more. We could say 1/3 to the first power, which is just 1/3. By the way, you might notice that this was some of these problems are going pretty quickly. This worksheet was intended to be something you guys were to work on in groups, but I'm just going to work through it for you guys right now. 1/3 to the -3 power. Well, that's the same as 1 over 3 to the -3, which is 27. If you're wondering how I got the 27, what I did was I took the 3 to the -3rd, I moved it up to the numerator and made it 3 to the +3rd, which is 27. F of -1, that means we're taking an input of -1 into our function, 2 to the -1. That's 1/2. And then G and H, those ones, they're calculator problems, but one thing you can do is you can do a little bit of work in your head to kind of verify your answers. For example, for G, we have G of 2.231, so that would be 1/3 to the 2.231. That's going to be somewhere between 1/3 squared and 1/3 cubed, closer to 1/3 squared. So it's close to 1/9 essentially, closer to 1/9 than it is to 1/27. You could go ahead and you could plug that into your calculator and you get an approximate answer for that. I got approximately 0.086. I'm going to go to the to 3 decimal places because that's what you guys will do on the calculus test, the calculus AP test, when you guys are juniors or seniors. And then for part H, same idea. F of 4.677 is just 2 to the 4.677. That's just a little bit less than 2 to the 5th, and 2 to the 5th is 32. So I know it's just some number slightly smaller than 32 and bigger than 16. So go ahead and plug it into your calculator. You get a decimal approximation again, and you get 25.5 581. I rounded to 3 decimal places again. Okay, so that's inputs and outputs for exponential functions. Main idea to take away from this is it's all right for the base of your exponential function to be a positive fraction. It's okay for your base to be a whole number. The one thing we want to make sure is that we restrict our base of our exponential function to be positive. It causes problems if we have negative bases. That's something we could talk more about in class, but for now, why don't we just do a little bit of graphing. Okay, so problem number 2 says graph f of x equals 2 to the x power. Part A has some good advice. Make a table of key values, an input-output table, and it says include both positive and negative inputs, and I think that is important. X and Y. I'm going to pick a couple positive ones. I'll start at 0 and build up some positive ones, then I'll throw in a couple negative values just so we're kind of complete with our graph. Maybe 0, 1, 2, 3. Those are some perfectly good inputs into my function f of x. And then I do want to try a couple of other ones, maybe just -1 and -2. That should be enough. Okay, if I input 0 into my function, my output is 1 because 2 to the 0 equals 1. If I input 1, my output is 2. If I input 2, my output is 4. If I input 3, my output is 8. And then in the other direction with negative inputs, remember I'm getting fractions. This is going to be 2 to the negative first power, which is 1/2. And if I input -2, then my output should be 1/4. Okay, that's more than enough points to get a nice graph. So I guess at -2 I'm at 1/4. At -1 I'm at 1/2. At let's see, at 0 I'm at 1. At 1 I'm at 2. At 2 I'm at 4. And at 3 I've made it all the way up to 8. Exponential functions, you guys will notice, grow very, very quickly. They start out small, and then very quickly they grow. It's important to note where your y-intercept is. We have a y-intercept at the point 0, 1. Some other things that you might notice is this graph has a horizontal asymptote, and that horizontal asymptote is at the line y equals 0. Now we know that there's a horizontal asymptote at y equals 0 because if you look at your original function, f of x equals 2 to the x power, there's absolutely no x value, no inputs that I could put into this function to get 0 or any negative numbers out. 2 to the x is always greater than or equal to 0, which tells us that we have a horizontal asymptote at y equals 0. There's no vertical asymptotes, though. No vertical asymptotes. The domain of this function is from -infinity to infinity. I could plug any value for x in that I want, and I'll get an output for the function. The only thing is the outputs are always bigger than 0. In fact, I said that the 2 to the x is always greater than or equal to 0. Actually, it's always strictly greater than. So this gives us our range, the thing I'm circling right now. 2 to the x is always greater than 0. My range is from 0 to infinity, not including 0. Okay, so there's some details about this function. Another thing you want to know about exponential functions is that they grow very, very quickly. This grows very, very fast. Okay, and that's true when we have a whole number base and a positive exponent. Let's try some others. Why don't we try f of x equals 1/3 to the x power? We're going to make our table of key values again, an input and output table. And I'll try a couple positive values, but I don't want to go too far with that because positive exponents on 1/3 are going to get very, very close to 0 very, very quickly. So I think 0 is a good input. I think 1's a good input. I think 2's a good input. We also should try some negative inputs, maybe -1, -2, -3. If I input 0 into my function, that's 1/3 to the 0 power, so that's just 1. If I input 1 into my function, my output is 1/3 to the first power, just 1/3. If I input 2, I get 1/9. If I try some negative inputs, well, 1/3 to the negative first power is actually just 3. So if I input -1, my output is 3. If I input -2, my output should be 9. And then I'm already off the graph by the time I get to -3. If I input -3, I'm already at 27, way off the graph. Okay, let's get an idea of what this looks like. Looks like I still have a y-intercept at 0, 1, so the y-intercept is still at 0, 1. Let's get a couple other points. 1, 1/3. Man, this thing's shrinking really, really quickly. By 2, I'm at 1/9. It's very hard to even graph that. Then -1, 3, -2, 9, and then I'm already off my graph. This function is going to look similar to the previous one. It's just kind of flipped about the y-axis in a way. I mean, it looks similar. It just looks like it's kind of flipped a bit. And that's exactly what's happening, in fact. We still have a horizontal asymptote at y = 0. There's still no vertical asymptote. But what you're going to notice is going to the right, this thing tends to 0, to y = 0. And then going to the left, this thing is shooting up to infinity. So it's getting very, very positive in this direction. And that's in contrast to the one we just did, where the growth is occurring to the right. So if you want to compare and contrast problem 2 to problem 3, problem 2 grows very quickly as x grows, and problem 3 tends to 0 very, very quickly as x grows. As you tend to the right, this is tending to y = 0 very, very fast. Now, if you notice, I remember I said that these two graphs kind of look like reflections about the y-axis, the line x = 0. The reason that they look that way is f of x for problem number 3 can be expressed in a different way. I can think of f of x as 3 raised to the -x power. And that would be a reflection of the graph g of x equals 3 to the positive x, right? When you take the opposite of the input, the transformation to that function is a reflection about the y-axis or the line x = 0. So you could see if you have a positive x or a negative x, if you have a reflection relationship there. These are reflections about the line x = 0. Okay, anyway, that's just some interesting details for problem 2 and for problem 3. Main thing to just take away from problem number 2 is as x gets large, the y value gets very large very quickly. In contrast, for problem 3, as the x value gets large, the y value tends to 0 very, very quickly. Okay, just a couple more.